Okay, so 7 is a similar one of these like maximization, although you don't have a constraint equation. To be fair, often, although I guess not always though, in this particular problem, actually they did have a picture, but I feel like you might not necessarily be given a picture associated with this. So in 7, it's talking about you're starting with a 16 by 16. Oops, which that is definitely not looking. 16 by 16 would be a square. So let's make it so it actually looks somewhat square-like. So 16, 16. That's the original. And then you're cutting out square corners. So meaning like equal, so little squares, exactly what it says. And you're doing that to create this box. So think of like, so these pieces are going away, right? And then you're just putting up the flaps to create a box. I mean, I am the worst at creating 3D. Let's see if I can do this. Oh, God, Danielle. Oh, that's total crap. So think about like, maybe I can do this. So these green dotted lines, so the flaps are coming up with this now. This here would be the new base. And then all these flaps are coming up, right? So you've got the new base and all those flaps are coming up to get this box. So the new base is this piece here. So let's think of the dimensions of that new base. I'm just going to draw it here. Originally, it was 16 and 16, but it's saying that originally this cardboard box, but let's see what we took out because it says that it cut out these squares. I don't know. Oh, I know why this could be confusing for you because it didn't come with a picture, but I should have said squares of length X. So X coming out here. So all these are X. So you're cutting out squares X and X. So it's a square, so it's X all around, right? So now if I think of the new dimensions of my base, it's no longer 16. I'm subtracting out X and X, so that's why it's 16 minus 2X. Same here, the other dimension also will be 16 minus 2X. In terms of how the height of the box, well, remember all these pieces are going up, all these flaps, and what is the height of all those flaps? It's X. So height will be X, and it's asking for the largest volume. So volume will be length times width, and it's 16 minus 2X times 16 minus 2X times X. So FOIL that out, find the first derivative, set it equal to 0. Then find the second derivative to make sure you figure, oh, actually, let's do this because I want to show you something that comes up in this problem. So I'm not going to really go through the derivative. I'm going to tell you what it ends up being. So when you do the derivative, you end up with 256 minus 128x plus 12x squared. Again, setting that equal to 0. And then I notice, let's simplify by dividing by 4 before I factor. 64 minus 32x plus 3x squared. Again, you probably aren't going to have this big of numbers, but factoring this, I got 3x minus 8 and x minus 8. And so I got x is 8/3 or x is 8. And so one reason you'll see that I crossed out 8 is like 8 doesn't make sense as even a possibility. You could try it by plugging in the second derivative, but look about if x is 8. This dimension would be 0, which doesn't make sense at all. So I'm going to try 8/3, and then you do the second derivative and see, okay, let's do the second derivative, and when I plug in 8/3, am I getting something negative? Because then that means it's concave down, so 8/3 would be a max. So 8/3 ends up being that x dimension that maximizes the volume. All right, let's do Let's do 8. 8 is, you could definitely have something like 8. I mean, maybe the numbers aren't, these numbers actually weren't too bad, but you could have something like 8. So you've got a storage shed that is a box with a square base. All right, so always draw if you can. So you've got this square base. I'm gonna try to make a box if I can. So square base means same dimensions. And then let's see if I can, I'm sorry, I'm trying to draw this properly here. So I got my square, actually, all right, I'm not going to label it yet. Let me just draw a box and then I'll put labels to it. So if I've got this square base, then, and let's make, I'm going to dot some things to make this the base. Okay, so the square base, and it's saying nothing about the height of it, so let's just give it some random height y. It has to be a volume of 100 cubic feet, so that's your constraint. The volume has to be x squared y, base times length times width times height, and that has to be 150. So that's your relationship between the two variables. Okay, so then let's see what else we got. The concrete for the base costs $4. Okay, so we're talking about something to build it with. So we're talking about areas here. So the area of the base is x squared, and so I know that that's $4. So $4 times x squared. The roof, which is also going to be, this roof here is also will be x times x. That's going to be x squared is that area, but now it's $2 for the roof. And the sides, all the sides are going to be x times y, and there's going to be this side, that side, the back, and the front. So there's 4 of them. So 4 of those sides, and their cost is $250, so 2.5, and then the area is x times y. And that's going to be, we're talking about our cost. So that's going to be the cost of everything. And it's saying, find the dimensions of the most economical shed. That's just a weird way of saying, or a fancy way of saying, find the dimensions that will minimize cost. So that's what you're doing. You're trying to minimize cost. Okay, so actually, let's clean this up. It's 6x squared plus 4 times 2.5 is 10. And notice it's in terms of 2 different variables. In order to take the derivative, set it equal to 0, I want 1 variable. That's bringing us back to my constraint equation, the relationship between the two. So let's solve for y in terms of x, and then I can plug it in so my cost is only in terms of x. So I've got 6x squared plus 10 times x times 150 over x squared. So I would, before taking the derivative, let's just simplify, because that x will go into the x squared once. So this is, and 10 times a 50 is 1500. And I'm just going to write it as x to the negative 1. Then I can use the power rule when defining the derivative. So now find the derivative, set it equal to 0, solve that, see if you indeed have a min by taking the second derivative. And if you do, that's going to be your x dimension, and now you just have to go back to that constraint equation and find the y dimension.